Thank you very much for your time, and thanks for inviting me for this prestigious event. My topic is use of stabilizing geo-grid for pavement optimization on highway projects. This is new technology, innovative technology, and there are several countries around the world, from USA, Europe, Middle East, Far East Asia, where this technology has been successfully used for the benefit of highway projects. My presentation is a bit long, but I'll do my best to cover it within 20 to 30 minute time. So don't want to be a barrier for the dinner, for the lunch. So I'll go through some introductory slide, and I'll go very quickly through the introductory slide. And then in the second part, we will look at the geo-grid application in highway pavement. There is a lot of research work built into my slides. I'll show you some very quick video clips, and then we will see how we can implement this mechanically stabilized layer concept for the highway benefits. The general problem for the highway industry, we know we have everywhere budget is limited. The authorities have limited budget, they want saving. Time is also a big constant nowadays, the project to be completed well in time. And then the materials, they decay. We know pavements are not, they are not designed to last forever. They are designed to fail, actually, I would say. The pavements fail after 20, 30 years time. So these are few problems. The highway pavement engineers, they want extended life. They want reduced whole life cycle cost. They want initial construction cost to be very low. So these are the highway industry problem in general, everywhere, applicable in Pakistan as well, and all part of the world. So what industry wants? They are probably looking for perpetual pavements. They last forever, which is unfortunately not available at the moment. They want whole life cycle cost to be reduced. They won't finish their project well in time. So this all are industry requirement. And like in the first session, Honorable Chief Guest, he said, environment is important. So we need to protect our environment. We want green type of solution for highway industries. So all these problems, they want innovation. Without innovation, we cannot address all these problems. Problem in the field for the pavement engineers, highway engineers, we have weak foundations, they fail. And then we have got ultra weak soils where we cannot move, we cannot mobilize manpower even. This was a project in early 1980s in USA. And the highway alignment was supposed to go over this kind of sludge area.
With Geo-grid, it was a different story. Only 2 men were needed, and it supported their weight.
So that's the difference the geo-grid can make. It allows the access to inaccessible areas. And then when we place the geo-grid, we can top up this with the soil. We place another layer of geo-grid. You can run your lorries, you can run your truck, and it offers you a competent foundation for the rest of the construction. Another type of ultra-weak soils, the failure happen on ultra-weak soil when the heavy machinery goes on top. Eventually, it results in a disaster. Other familiar pavement problems are cracking. It can be due to several reasons: the thermal cracking, fatigue cracking, and it can be material issues as well. Pothole is very common phenomena, failure phenomena in the highway industry. And then we can see differential settlement, wavy form of highways. And we want competent highways. One of the example, for example, there is a project from Sargodha to Silawali project that is going to be constructed using rigid pavement, which is extremely expensive than the flexible. Probably the problem at the site is the alignment goes over a variable type of soils, which eventually will result in a wavy form of construction. That's the reason probably it is proposed that the government want construction using the rigid pavement. But there are solutions. We can avoid the rigid pavement, construction, which is extremely expensive. We can use innovative techniques, we can reduce the cost while getting the same performance. Rutting, it is a structural failure of pavement. This is an indication. It might be local failure as well, but it indicates that there might be problem with the pavement layer itself as well. So what we want to see, we don't want to see all those problems. Highway pavement engineers, we want very competent roads with high level of serviceability. That's kind of requirement for future highways. So how we can achieve this? We can achieve this kind of highways if we adopt innovative technology. That's the only solution. At Tensar, we have done innovation. The word geo-grid today I'm using, and many people they use in their presentation, that actually come from Tensar. Tensar is the innovator of the word geo-grid and the geo-grid itself. So this is the latest technology in geo-grid. On the background, you can see hexagonal shape of product. This is called Tri-X. It has got several advantages when we use in the highway construction design. We will go through some research work as well. This product has got innovation awards all over the world. IGS 2010 in USA, Better Roads Award in 2010 in USA again, IGS Award, Gold Medal Award in Poland, Czech Republic Award, and NC Innovation Award at Civils UK. Typical benefit when we incorporate these layers of geo-grid into the unbound materials, the typical benefit we are looking for is reduction of pavement thickness up to 50%. What does it mean? It means that if we can reduce the thickness of pavement, we can speed up the construction projects, and we can save 50% of construction time as well. It has got the capability to increase the design capacity by 100%. It can decrease the construction time by 50%, as I said. It can improve health and safety and cut carbon emission by 50%. So for some of those who don't know the geo-grid, what is a geo-grid? When I say geo-grid, some people, they may not know what is geo-grid. So this is an open grid-like mesh structure. This is made of polymer material, HDPE, PP materials. It is stiff. It has got stiff integral junctions, ribs, aperture are sufficiently large to form the interlock with the construction material, which is the aggregate. And these geo-grids, they are used for reinforcement or stabilization of soil. We will see what is reinforcement and stabilization. These are two different functions of geo-grid. So there are few types of geo-grid: biaxial, uniaxial, and hexagonal geo-grid. The manufacture of geo-grid, it is formed by the polymer sheet. Polymer sheet goes through a punch machine where it is punched, and this punch sheet is stretched into two directions to form this grid-like integral structure. Next slide is a very quick clip that shows how these punch sheets are stretched in one direction. The first video shows stretching in one direction, and the second shows you this stretching of this point HDPE sheet into the second direction. And as a result of this punching and stretching, this happens under very controlled environment, very controlled temperature, very controlled loading. So we get this kind of structures. In terms of application, these have got extremely variety of application into the highway project. One of the example is the retaining structure, like Dr. Sohail Kibriya, he mentioned reinforced salt technology. This is another alternative to the reinforced concrete technology, which is cheap, quick to construct. This is one of the project in Dubai, highway project, Dubai to Fujairah. This is 60-meter high structure into 3 tiers, 20 meter each. It can accommodate culverts up to 4 meter by 4 meter. There are 4 culverts. This is probably one of the biggest project, highest walls in the world. The total area constructed was about more than 100,000 meters square of wall face area. One more application, like access over ultra soft soil. You have grid, you don't have grid, you can see the difference immediately. So it allows you the access onto the site. And if this geo-grid is topped up with soil, then you can run your lorries on top of these kind of weak soils. Heavy duty pavements, railway structures, working platform, unpaved road carrying heavy machinery like wind farm, unpaved roads, airfield, and then finally paved roads and highways. So next slide, they will focus on paved roads and highways. So let us see the structure of a pavement, typical pavement. It has got 1, 2, or 3 asphalt layers. It has got road base, road sub-base, and then eventually we have got existing soils which form the subgrade. The material quality increases from bottom toward the top. Subgrade is the weakest, while the asphalt is the strongest material in terms of construction. When wheel passes on top of pavement, what happens? It applies load onto the surface of the pavement, and this load distributes through the different layers of the pavement and eventually end up at the existing subgrade, and it exerts certain stresses onto the subgrade. Let us quickly see the failure mechanism that might happen during the life of the pavements. When wheel passes on top of pavement, the pressure because of wheel, it start moving the unbound and bound particles into different direction. In a simplified format, the aggregate particles, they start moving downward, they also start moving laterally, and more interestingly, rotational type of movement also happens into the aggregate layers. And it causes deformation at the subbase, and it also causes big deformation on the surface. That is kind of structural failure of pavements. What if we place a layer of geo-grid at the bottom? What happens? This geo-grid interacts with the soil particle. It offers the confinement to the soil particle, and as a result, the disturbing forces get the reaction from the geo-grid. The geo-grid interlocked with the soil particle offer reacting forces. So it keeps the particle into place, it restricts their vertical movement, it restricts their horizontal movement as well as rotational movement. This is concept. We will see in real time whether this is true and how it actually acts. So as a result, the deformation still happens because, like I said, pavements are designed to fail at the end of the day. The deformation, the level of deformation is very small as compared to the unstabilized section. So let us see quickly DEM modeling carried out by Ateska Engineering Consultancy in the Germany. They model particles, they model geo-grid into their system, they validated their assumptions in the lab. So the DEM model is developed based on some assumption. Those assumptions are validated into the lab to make sure that their model is perfect. And then they run the model into DEM type of modeling. And we can see on the right-hand side is unstabilized section. Red color indicate failures, movement of particle, horizontally, vertically, rotationally as well. While the other section at the bottom, that with most of the color is green, green shows restricted movement. There is still movement, but it is very restricted and it is not dangerous from failure point of view. So there were 10 wheel crossing. This kind of research took many years. This is not done overnight, or it is not done in a few weeks' time. It took about 2 years to model this DM modeling, then validate it, and then again run it and get the result. Ninth run of the model, on top is non-stabilized section. You can see the red, the movement of the particle vertically, and then at the bottom is mechanically stabilized with hexagonal geo-grid, and you can't see red color because the movement is restricted. Now look at a small video clip. When the wheel passes in this model over the grid, we can see the tension in red color. The blue color is compression. So part of the grid directly beneath the wheel, they are in tension. So if I use a simplified model, actually the wheel creates tension ring. That tension ring goes through the whole pavement layer, eventually end up at the subgrade level. So what we need, if we have got a product at the base of this unbound material that restrict this tension ring and reacts with against the tension ring, we can get better performance. I'll show you one more research work, piece of research work that will show you the rotational kind of movement that happens in the aggregate layer. This research work was carried out at Penn State University in USA. On the right hand side, you can see artificial rock. This is called smart rock. It has got sensor into it. It has got the capacity to record linear, translational, and rotational movement directly. So I'll show you the real-time movement that happens into the aggregate layer. On the left-hand side is the real rig. Rig operates, and as a result of the cyclic loading, without grid and with grid section, you can clearly see the movement of particle. After certain time, this movement will increase in the unstabilized section, while the stabilized with the geo-grid section, still the particles start rotation at their own place. They don't leave their place. So red color was their original place. You can see on the left hand side, without geo-grid, the particles start moving and start going away from its original position. And these kind of rotational, translational movements, they cause the deformation and rutting into the pavements. I'll move on because we have unfortunately short time. This is the graphical representation of Penn State University research. On the vertical axis, you can see particle movement, acceleration. On the horizontal axis is the time. Just after 500 seconds, different color represent movement in different axes, X, Y, and Z axes. On time scale, after 500 on left-hand side, without geo-grid section, you can see a lot of movement of particle. While on the right-hand side section, you can see there is a movement, but it is very restricted movement in all three directions. This is translational movement of particle. Next slide shows you the rotational movement of the particle. On the left-hand side, again, without geo-grid, a lot of variation, a lot of movement of particle. With grid, there is very limited angular movement. Let us see on the load spread that I mentioned in my previous slides. Wheel passes, we know it applies load. That load is distributed through different layers and eventually applies stresses on the subgrade. What if I place a layer of geo-grid underneath? Wheel passes again, applies pressure, but this time the load distribution is a lot, which means the stresses at the top of the subgrade, now they are reduced because the load is same, area is more, so we know area is more, load is same, we have got reduced stresses. So these reduced stresses protect the subgrade. So there is no deformation in the subgrade. We remember the original was very causing into punching type of failure, while the wider area does not cause punching type of failure. So this is again concept. Now we will see the validation of this concept through research work that was carried out at BRE 2007 and 2010. Most of you would recognize BRE in the UK. This is independent testing lab, one of the biggest testing lab. It has got a 3-meter ring, concrete circular construction area, which has got grid in it, compacted soil, and here is the graphical representation of the test section. Apply 35 kilonewton load, and we can clearly see the load distribution through the granular layer going to the weak soils forms a kind of punching type of failure. Like I said, we put 2 layers of geo-grid, we apply 84 kilonewton load, more than twice the original load, and it gives us the wider area at the base. So these, you can see the contour lines, the pressure diagram, the pressure lines, and it clearly indicates that the load distribution through granular layers is more this time. From all this research work, we have develop a concept called mechanically stabilized layer, or simply MSL. So this is same concept, grid interlock with the aggregate, and it forms a composite structure. Like Dr. Sohail Kibriya mentioned, that there is some similarity with the RCC structure. Reinforcement reacts, form a bond with the concrete, and we get performance, better performance. Similarly, we have got aggregates, we have grid, it forms, it interlocks the aggregates, and as a result, we get a composite property of that layer, MSL layer. And the properties of this composite layer, it has got enhanced properties, better performance than individual pieces of grid and aggregate. So that's MSL, granular layer plus grid, we get a composite layer, and this composite layer we call it MSL, whose performance is, which perform about 1 to 5 to 2 times more than a bigger, thicker, unbound layers, which indicates that we can replace bigger granular layer with the thinner granular layers. This MSL concept has been recognized by European Organization of Technical Approval, which defines that it works through lateral constraint, confinement of particle, and that confinement offer interlock to the particle, which restrict their movements. As a result, it offers radial stiffness, because we know the load is radial, all 360 direction. So this is published document. You can get access through website, Google it, IOTA report TR41. It defines stabilization function, it defines MSL, it defines the test procedure for the geo-grid testing. It also defines the method of, it offers distinction between reinforcement and the stabilization function. I mentioned before, there is another function that is called reinforcement mechanism. This is, we are talking about pavement structures this time. We are not talking about reinforced soil walls. So that is different. Within the pavement layer, we have got two distinct functions. One is stabilization, one is reinforcement. For any type of reinforcement product to perform, they also perform. Stabilizing geo-grids perform, reinforcement geo-grid perform when incorporated into the pavement layers. The difference is any reinforcement that need to perform into a pavement layer, it need to go through tension membrane effect. It need to go under deformation to pick up the load. If it doesn't go through deformation, it doesn't pick up the load, which means it is not performing. So that's the key difference between two mechanisms. Of course, the highway engineers, pavement engineers, we don't want deformation in the subgrade, and also we don't want deformation on the top of the roads. So I'll skip this one, this incorporation of geo-grid into pavement layer to get the benefit of cost, to get the benefit of speed. All this is called pavement optimization. So I'll spend a few seconds on this slide. So what kind of benefit and how we can, in a different ways, we can get benefit from the geo-grid. So on left-hand side is a typical section of pavement with 4 inches of asphalt and 10 inches of aggregate base course. It has got some design life. The second section shows you reduced asphalt thickness, which is 3 inches, and reduced aggregate thickness, which is 7.5 inches. The left-hand section and the right-hand section, they have got same performance in terms of load carrying capacity. So it means we can reduce the thickness of the pavements, and we can use innovative technology to reduce the thicknesses. Moving on to the next one, the next section show a little bit reduction in the asphalt, now this time 3.5 inches, a little bit reduction in the aggregate course, which is 9 inches this time, and the performance has increased 3 times. These small reduction, they can justify the cost of the grid, while the performance we are increasing up to 3 times. So still we are getting benefit. In the last section, we are adding a bit of cost of geo-grid. We are using geo-grid while sticking with the old original section. The performance in this case increases 6 times. I'll quickly go through it. Pavement design, we know this is all empirical design. Originally, the ASHTO was based on 1952 road test carried out in USA. It went through a lot of modification, and eventually we have got latest ASHTO codes. So the point is, ASHTO code, all other design code all over the world, they are empirical, which means they are based on the experiments. The empirical design using Geo-grid, its history goes back to 1980s. When first time the Geo-grid was tested at Oxford University, and they recognized there is a benefit of using Geo-grid for highways. I won't go through the Oxford research work, but typically the research methodology, the research work starts from in-house labs. We carry out in-house testing, we get the confidence, we go to independent lab, we get more confidence, we apply this into the field, and we carry out site testing, and then that is successful, and then we go for the large scale, full scale, accelerated pavement type of testing, or accelerated plate load testing. These kind of all testing have been carried out at independent institute like TRL is very extremely popular in pavement engineers in the UK, ITESCA in Germany, BRE in the UK, University of Illinois in USA, US Corps of Engineers, Nottingham University, ERDC, Research and Development Corporation UK, Kansas University, University of Massachusetts, and Penn State University. There is a lot more research than this one I'm presenting, I'm showing it. So different type of research is carried out, modeling, lab test, static load, dynamic plate load test, wheel load test, full scale test. We have carried out all these kind of testing, and on top of this testing, there is a site validation to confirm the original assumptions, the original testing in the lab, whether they are realistic on the ground as well. These are photographs of some of the facility around the world. Then TRL testing, I would say this is one of the biggest research work carried out in the world. TRL 1 started in 2001, and eventually TRL 8, we finished this kind of testing in 2013. We monitor different grids, biaxial, hexagonal geogrid, and we can see the performance. I quickly go through only US Corps of Engineers research work in 1992, 2000, and then 2000 recent research work. So this is the original 1992 kind of facility available at US Corps of Engineers. It was carried out by 133 kilonewton wheel. Typical wheel load we know is 40 kilonewton, standard axle is 80 kilonewton, but this research in 1992, many years ago, was carried out using 133 kilonewton. And it was carried out to compare different products. Woven geogrid, extruded geogrid, then there is control section, woven punch and stretch, and then punch and drawn grid. And on the left hand section, you can see the number of passes to achieve 25 mm rut depth. So criteria was set as 25 mm rut depth on top. So this is again US Corps of Engineers 2009. I'll show you a quick slide, the real-time testing at US Corps of Engineers. This is again 133 kilonewton loading from the wheel. This is almost the same wheel as we have got front wheel of aeroplanes. Tandem axle. So it is reported, it is published by Tingle and Jersey in 2009. It was full-scale accelerated pavement testing. The aim was to collect the performance data, and then based on that performance data, validate the design approaches available. Project was carried out into two phases. One phase, the subgrade was CBR 3%, the other CBR 6%, and we could clearly identify the traffic benefit ratio, the load carrying capacity of the stabilized versus unstabilized was about 5 times. This is the cross section of US Corps of Engineers. Different items. One was grade, one was control, and one was again control but with thicker pavement. And we can see the difference from the graph, the performance of A, B, C. A section is Geo-grid, B and C are control section. B is thinner, C is thicker. Of course, the thicker performance is more, thinner performance is less. But on top of both these sections, the stabilized section perform a lot better than these thicker and thinner sections. So this is the real photograph from the site after excavation to see the deformation. This is US Corps of Engineers 2012, 5 sections. Actually, I'm just showing you 2 sections. A bit thicker asphalt course, 4 inches and 3 inches with the Geo-grid, 8 inches unstabilized, 6 inches of aggregate with the stabilized, and both perform equally. And if we look at section A and B, on the left hand side, the upper table, and then the last column, 200 E cells. And this 0.25 and 0.28 is deformation. After 200,000 E cells, the deformation of both sections stabilized versus thinner stabilized versus thicker stabilized is almost same. These are some photographs from the site. I won't go through case studies. There are thousands of case studies available where these type of technologies has been successfully used to benefit the highway projects. This is one of the case studies in the UK where the client used this technology and they saved more than £500,000 worth of saving from site. And at the same time, on top of saving, the design capacity was increased from 21 million up to 52 million standard axles. So in terms of acceptance, this has been, I said, widely used all over the world. AASHTO R5009, again a public document, you can get access. It gives the methodology of designing. Then European organization, US Corps of Engineers, several testing. Then Texas validation on site. There is one small piece of research work at UET Lahore that was done back in 2007 for the proposed Sialkot motorway project. Unfortunately, that didn't happen at that time. Then these all methodology, design methodology has been validated by a consultant called ARA, independent consultant in the USA. Then National Cooperative Highway Research Program in the USA, two documents, public documents, you can get access. UK Highway Agency, and then again Texas, and then the last one, this one is a research work in Singapore. The title of research work is Decreasing Construction Speed of Road by Using Geo-grid. The one aim only, how to reduce the construction time. Then highway magazines, GMA White Paper 1, GMA White Paper 2, and then NHI, FHWA. So what we have got, we have got design tools to carry out designs of pavement. I am happy to offer all of you, if anybody is interested, you can contact me, and I am happy to give you training on this software. I am happy to provide you the copies of this software free of charge, and I am happy to provide you training as well, how to design these pavements using grid technology. This is another software, 2 pieces of software for pavement design. You can compare non-stabilized versus stabilized section. This is based on AASHTO design methodology. And this software, both of these software has been validated by ARA. Their methodology is validated. So what we get? The key benefits: improved construction thicknesses, improved capacity, improved service life, reduced risk, improved serviceability and reliability, improved contractor program, and improved carbon emission environmental saving. And then there are some other benefits which I'm not going to go through, and I think that's it. And I'm happy to take your question during lunchtime. Here is my contact detail. You might give me a call, drop me an email. I'm based in Kuala Lumpur office. Thank you very much for your time.